So this is a slideshow basically.
Mm-hmm.
So our project basically used AI and it
Mm-hmm.
created an inference engine that can determine how a projectile was launched using only time and position data. This includes like velocity, the drag coefficient, which is also known as air resistance, and
Mm-hmm.
the angle from which it was launched, and the noise, which is basically like when you send an object, there's always going to be noise, which is like when a sensor has to track the object when it's moving from one point to another in the air. So noise is basically like wind that could possibly not be accounted for, like the sensor maybe being shaky. So those type of things are like noise basically.
Mm-hmm.
So our our inference engine takes all that data and it generates a graph of the sensor data based on what we give it, and that's just plotted as points. And so all our AI does is it looks at those points and it has a prediction of the velocity, angle, and area since there was when the object was launched.
Okay, understood.
And so we previously went over the problem. I'll say it again. So if in a lot of real world scenarios, objects are launched, but we don't know from where and at what speed they were launched from. So basically, what our project aims to do is allow people to know what velocity and air resistance and angle an object was launched from for a bunch of real life uses such as like military or like even in sports, like you can find out the angle and velocity from which like a basketball was thrown, like things like that.
Understood.
So basically, we followed a modular pipeline. So the user can upload the data of their projectile trajectory through the web interface, specifically Streamlit through Python,
Mm-hmm.
and it's basically processed and clean to make sure there's no extra data and to ensure the columns and rows are all lined up for the model to know, and the model gives an initial estimate, and then that's the initial estimate is it goes through an optimizer basically, which uses strict calculus, and it basically narrows it down to a specific measurement of the exact velocity and drag angle the object was thrown at.
Okay, understood.
So basically, real data on this type of stuff is very difficult to obtain because it's a very broad category. Like there are a bunch of projectiles launched daily from like anything. It could be like you throwing a ball, like missiles launched. Like it's a very broad category.
Yeah.
So basically, we decided to generate synthetic data using a Python script. And so this synthetic data uses physics equations and it uses drag coefficients and it basically uses lines that are already generated of things launched from certain velocity, drag, and angles. And so the model is able to look at that and train itself by basically it gives it the velocity, drag, angle, the drag and the angle, and the
Mm-hmm.
model makes a prediction and then compares that with the already existing correct answers in the data set. And if it's right, it continues on that same pattern until it gets one wrong and it fine tunes itself. So basically the model does that until it gets its accuracy to a level that you desire. So yeah, that's basically how we tracked it.
Understood.
And then um yeah, the ML model, it also it estimates the parameters that created the data. It's just expanding on the last slide. And this is where the initial guess comes from. Like the it gets optimized in the next step, but the initial guess comes from the ML model, but then it uses math to optimize it in the next step. That's the difference.
Oh, understood.
Yeah, so as I was saying before, so it passes into a physics simulator that solves the equations for the AI, and
Mm-hmm.
basically the gravity and air resistance are what's like modeled, and then it optimizes it and it adjusts them to like fine tune it and get the least amount of error possible between simulated and observed.
Understood.
Because the ML, all it does is it just finds out the data based on the numbers that are already there. So for example, it could give data, but it might not be like correct according to physics. It could just be
Mm.
numbers, but like according to physics, it might not even be possible. So that's what the optimizer does. It makes sure that it's possible according to physics.
Understood.
Yeah. So this was my partner worked on, but I can give an overview of it. So the LLM is basically, LLM is a large language model like ChatGPT, Gemini, like it's basically able to reason and give like analysis on its own.
Mm-hmm.
So this does not perform any calculations or optimizations. Basically, in our app, once the data is done, there's a second section on the side that says inference, and that gives the data. So just how off was the AI from the actual thing, like the errors, like for velocity, angle, and drag, it gives the error. And so basically, the LLM takes that and it analyzes the results, like how good was the accuracy, what does this mean, like what is velocity, what is drag coefficient, so it's easy for users to understand even if they haven't seen anything like this.
Understood. Understood.
Yeah. And so yeah, basically this was our final product. So we also did throughout the project, we also stress tested it to check which noise level would really like make it start hallucinating, and like the cutoff was before it started giving incorrect data. And we got it to like a noise level of around 2.5. So we just capped the scale from 0 to 2.5 for the noise level. So
Oh,
yeah, so the final application just it displays a graph with the sensor data, the AI prediction, and the true path of the object. So the
okay.
AI is only able to see the sensor data, and it's able to predict the velocity, drag coefficient, and the angle. So yeah,
Oh,
basically it combines like ML, LLM, and like basic Python like data generation through scripts.
okay. Understood. All right.
Yeah,
Uh, well, nicely presented. I understood
yeah.
what you were trying to say. Okay, one question though. If you had to explain this whole process or the whole project to a second grader who does not know much about physics or AI as such, how would you explain in simple language?
Mm, like a like very brief summary, or should I just say like the entire
Just
project?
simplifying it. If you are explaining, imagine I am a second grader now. Hello.
Okay.
So if you had to.
So basically, a projectile can be anything. It can be a ball. It can be a ball, a can. It's something that you're able to throw and that follows a path. And imagine when you throw a ball, it goes up and then it comes back down. So
Mm-hmm.
that's basically the path that the projectile follows. That's what it's called. The projectile
Understood.
is just the ball or the object that you're throwing. So
Mm-hmm.
when you throw the ball, the the ball you throw it at a certain speed. You can throw the ball fast. You can throw the ball slow. So
Mm-hmm.
that speed that you throw the ball at is also known as velocity.
Mm-hmm.
So that can be measured in miles per hour, kilometers per hour, meters per second. There's a bunch of different units to measure it. And so that speed that you throw the object at and the power you use to throw it is called velocity.
Understood.
Uh, so
And what
the
does the project exactly do?
what can you repeat that, please?
What does the project exactly do? What is the output that it gives you?
So our project, it takes data. So it takes the speed or power that a projectile is thrown at. It takes the air resistance in the air. For example, when you
Mm-hmm.
throw a ball, even
Mm-hmm.
if you throw it with the same power and speed, it will not always land at the same location. Even when you throw it at the same angle, it like
Mm-hmm.
from the same, like if you tilt it upwards or downwards, even if you throw it from the same angle, it will not always land in the same place. So there are
Yeah.
factors in the air such as wind, and things like that that contribute to the drag coefficient, which is also known as air resistance. So
Okay.
you can give it the speed and power you throw the ball, the
Mm-hmm.
what how up or down the angle that you throw the ball, and the amount of air resistance that is there when the ball is thrown. And you can
Mm-hmm.
also give it noise, which basically means there are a bunch of factors that you cannot control, such as to measure the path of like the ball that's being thrown, you need to use sensors, which basically track the path of the ball. So
Understood.
noise basically accounts for things that you cannot control in the sensor, like the
And
sensor movement, things like that.
mm-hmm.
So our project takes that data, the speed, the power the ball was thrown at, and it predicts the path the ball was thrown from. All our project sees is the sensor data, meaning it just looks like a bunch of dots simulating the ball, like where the ball
And,
was at the start, where the ball was at the end, where the ball was in the middle. So basically,
understood.
it takes that and it's able to draw out the exact path the ball traveled and from
Mm-hmm.
what power, angle, and drag coefficient it was thrown from.
Understood. Understood. Greatly explained. Nice. You have your demonstration ready? I want to see what it exactly does. So we'll get on with
Yes,
that.
I have the app ready. Wait, I
Yeah,
just have to get it a second. It was sent in the chat. Um,
sure, sure. Take your time. Sure.
here it is. Okay. Yep, this is our app.
Mm-hmm.
So basically, on the left, as you can see, there's a selection bar. So you can select the velocity, the launch angle, the drag coefficient, and the sensor noise. So let's just do this. So basically, you see the light blue dots here.
Yeah.
So that's basically all the AI sees. It does not see the dark blue line behind it. All it sees is these light blue dots. So the AI is just able to see these blue dots, and that's the true path the object traveled at.
Okay.
And so as you can see, once it lands, it bounces a little and then it comes back down. So from that, the AI, the red line, the AI is able to predict the exact path that it thinks the ball went at with the velocity, drag coefficient, angle it was launched at.
Okay. Understood.
The dark blue line behind it is the true path that the object followed.
Mm-hmm.
And you see how some light blue dots are below like the dark blue line. So you might
Uh-huh.
be thinking, how is that possible? So
Yeah.
that's basically what noise is. The sensor shaking and stuff, it causes the sensor data to be like below and on top of blue line, even though it's not the real path the ball followed. It's like you can't control that.
Understood. Understood. All right.
Yeah, so underneath you can see the AI scientific interpretation.
Mm-hmm.
It did identify that it had poor accuracy since our model has a tendency of overestimating velocity,
Mm-hmm.
but um the sensor noise was tuned decently high to 1.0, which is very unrealistic in real life scenarios.
All right.
But for the sensor noise and the data, it did a good job since the drag is also difficult to estimate in this scenario.
Understood. All right. Can you just adjust the parameters a bit and launch it?
Yeah. Like yeah, I try this. Yeah,
All
yeah.
right.
So our AI model also predicted it again, and so it showed varying accuracy. So the initial velocity was overestimated, but the launch angle drag coefficient only had moderate errors, and so uh it also includes like biases in the model, imperfections that are not accounted for, and
Mm.
like things that are challenging to estimate and things like that.
Okay. Understood. Well, it looks nice. Great UI as well. I just wanted to ask, does the graph change?
What do you mean?
Uh, the the trajectory, does it change?
No,
Graphically speaking.
no, it's all on one scale.
Okay. Okay. All right. Fine. Okay. Nicely explained. You can stop sharing your screen for now.
Yeah.